Today we're talking about the first law of thermodynamics, also known as the law of energy conservation. The law states that a change in internal energy of a system is equal to heat added to the system plus work done on or by the system. When examined more rigorously, this law actually outlines the relationship between internal energy, work, and heat. This law can be stated as an equation where delta U equals Q plus W. All of these quantities will be measured in joules. This means that the change in the internal energy of a system will be equal to the energy transferred to or from the system as heat plus the energy transferred to or from the system as work. Because of this law, we can outline three different types of processes that can occur. If a process occurs where there's no change in volume for the system, this means that no pressure volume work can be done on or by the system, so work is zero. In such a case, delta U equals Q. Any change in internal energy must be the result of heat transferred in or out. We call this an isometric process, meaning no change in volume. An example of this would be a bomb calorimeter, where a combustion reaction produces a change in temperature, but the rigid walls result in no change in volume. If there's no change in temperature of the system, there cannot have been any change in the internal energy of the system since these two volumes are proportional or the same. Therefore, delta U will be equal to 0, which makes Q equal to W. This means that any heat transferred into the system is used by the system to do work rather than increasing the internal energy of that system. This is called an isothermal process, meaning no change in temperature. An ideal version of a car engine would be an example of this, as the pistons ought to convert all of the heat energy from the combustion reaction directly into expansion of the piston that moves the car. If there's no heat transfer, Q will be 0 and delta U will be equal to W. This means that the internal energy of the system changes as a result of doing work on its surroundings or the surroundings doing work upon the system. Such a process will be called an adiabatic process, meaning no heat transfer. We can see this in certain processes in Earth's atmosphere, such as when masses of air change position due to pressure differences. If Q and W are both 0, meaning there is no heat transfer and no work done, there can be no change in internal energy, and this must be an isolated system. Returning to the equation, we need to define the signs of these quantities in order to use it properly. So let's note that when heat is absorbed by the system, Q will be positive, and if it is lost by the system, Q will be negative. If work is done by the system, like an expanding gas, work will be negative. If work is done on the system by the surrounding gas causing compression, work will be positive. If there is no transfer of heat, then no work is done. Both of these values can also equal 0, as we've previously discussed. When doing calculations, make sure that you use the correct sign for these values or the answer will be incorrect. For example, if 100 joules of compression work is done in a system, and as a result, the internal energy of that system increases by 74 joules, how much of the energy is transferred as heat, and in which direction? Let's take our equation and rearrange to solve for Q, which will be delta U minus W. We can then plug in positive 74 joules for delta U since internal energy increases, and positive 100 joules for work since work is being done on the system, and we should get negative 26 joules for heat. This means that as 100 joules of work is applied to the system, only 74 joules go toward increasing the internal energy of the system, while 26 joules are lost as heat dissipated out of the system. These kinds of calculations will happen a lot in thermodynamics, so let's check comprehension with a practice problem.